Hello, everybody. All right, so we are going into the beginning portion of integration. And so this is the way that we go into it. So we're going to just start by talking about what an antiderivative is. So this lesson is going to cover two main things. We're going to talk about antiderivatives and some basic properties and everything. And then we're going to talk about how to solve some differential equations. So let's start talking about antiderivatives. So when we first start out with integration, we talk about antiderivatives, and what we're doing is we want to know if I give you the prime graph, or if I give you the prime equation, where does it come from? What is the original equation in all this? And so we start off with the antiderivative, which is the same thing as the indefinite integral. Because you're not solving for anything, you're just trying to find a generic basis. We need to know the original formula. What could it possibly look like? What is that parent function? And so with that, we start taking a look at different properties. And so as we're going through this, just pay attention to the new notations and stuff that we're going to wind up having as well. So, definition of an antiderivative or an indefinite integral, either one, because they're both the same thing. Says basically, notice that it's a capital F this time. So, a function capital F is called an antiderivative of function, or little f, on an interval, whatever that is, if this happens. So, if f prime of x is equal to the little f of x. So you're going, huh? So basically what it's saying is this, is you're going to be given like the prime graph. You're going to be given the double prime graph, and you want to know, what does it look like? Where did it come from? So when you're going back and doing it, for instance, a parabola. So if we go through and I give you this problem, for instance, let me get a color. If I give you f prime of x is equal to, let's say, 2x. And I want to know where this came from. That's just kind of ugly, isn't it? Try again. X. There we go. When I do my antiderivative, and I'm going to show you how to do this here in a minute, I know that this graph, because if this is my prime graph, that had to have come from that. Because if I took the derivative of 2 or x squared, I wind up with 2x. But the problem is because when we take derivatives of constants, they go away. They get a derivative of 0. And so when you look at this graph here, so fine, if this is my function graph, my prime graph, my derivative graph, all of these possibilities plus a million more are actually my correct answer. And so we have to either be given more conditions, or we just look at some random plus c that happens here. Because we don't know what we have added or subtract from the actual original graph in order to wind up with this 2x. Because, for instance, if I gave you x squared plus 2, if I took that derivative here, I still wind up with 2x. Well, if I have f of x is equal to x squared minus 3, when I take that derivative, again, I wind up with 2x. And so that's why it's important to understand when we start off with these antiderivatives, these definite integrals, that there's technically multiple answers, but it's going to be based off your conditions that they have to give you in order to get the actual original graph. So before we move any further, if you need to pause the video right here, you need to do this. If you do not have these, you need to put these in your notes somewhere, and you need to start memorizing them. These are extremely, extremely, extremely important. Now, with the exception of 16, 19, 20, and 18. Those 4 are not going to be tested on the AP exam. The rest of them get tested on the AP exam. So those are the ones that you have to have committed to memory in order to be successful on the AP exam. All right. The other ones, you don't have to worry about it as much. And if you think about it, if you look at arc sine, for instance, remember when you take the derivative of sine, you get positive cosine. So this piece right here is going to be positive. But if you took the derivative of cosine, you get negative sine. That's why that piece right there is negative. So if you take a look, that 15 and 16 are virtually the same thing, except one's positive and one's negative. And that truly depends on if you're looking at sine or cosine. All right. So if you need to, make sure you're hitting that pause button and getting these written down. You need to put these into memory somehow, somewhere. All right. So now we're going to look at new notation. So as we go forward and we start doing the antiderivative of this stuff, we are going to be looking at different notations. So we are moving away from this notation right here, and we're coming into this notation here. Now, this is an elongated S. Anytime you see that in elongated S, you know that you are about to take the integral of something. Well, basically, you're going to go backwards. And you're going to find the original function. You're going to find the original function that this actually came from. So take note that we are no longer, you'll see this piece here sort of kind of a little bit more often because we're still kind of new into it. But eventually, once we're in integration, it's just going to be this piece here. All right. So here are some most popular indefinite integrals. So these are just your basic formulas, especially like this one here is a basic formula because this can apply to any power rule. But the rest of them are pretty much what you see is what you get. So take a moment, write these down, and then we're going to start playing around with some of these. Okay, so go ahead and hit the pause button now. All right. Let's see here. So now what we're going to do, plus C. So let's talk about this. This is probably the most important thing that you need to remember when you integrate is that plus C. Sorry. Unless they give you conditions, you must have this plus C, even if they give you conditions, because eventually what you're going to do is you're going to wind up solving for the plus C anyway. You have to have all this information in here, but you have to make sure that plus C is in here, because even if they give you the initial conditions that come from the original equation, without that plus C, you can't plug anything in and solve for it. So that plus C, when you do your indefinite integrals, that must be present in everything that you do. If it's not, I'm counting it wrong. And so will the AP exam. You must have the plus C there. When we get to definite integrals, that's something completely different. And we can talk about that at a later time once we actually get there. Okay. But for now, because we're talking about antiderivatives and indefinite integrals, the plus C has to show up. Okay. This is just a little bit cleaner version if you didn't like the other version. I don't know, I guess I forgot to delete this one. Doesn't matter. But it shows you the same thing as the other one just did. Okay. So let's take a look at this. So we have a couple examples here. So we're going to start off with this A here. So we have the integration of x minus 3 dx. Now that dx needs to go there because you're saying that this is actually the derivative of something. X minus 3 is actually the derivative of something. And so we're going to integrate to go back to the normal piece. So when you're actually taking a look at this, what you need to also remember as well is whatever letter's here, that letter also better be there as well. So it has to show up in both spots. Now, when you have a problem like this one here, then until you get more comfortable with it, I would, in your mind, think this. Oops, I did not. Well, I didn't want to do all that. Minus. Yep. This is what you need to do. Take these terms separately, because when you take these terms separately, then it's a little bit easier. Now, once you get better feel for it or whatever else, you can keep everything together and just do it in one big swoop. But until then, keep them separate. So now, how this works. So we're going to start off with this one right here. You need to remember that there's an imaginary 1 sitting there that you don't see. All right? So what we do, we're going to apply the power rule. And the power rule says if you are given this right here, in order to find out where that came from, you're going to add 1 here, and then you add 1 here. All right, so you need to make sure that whatever you do, you wind up with this. So if I'm looking at this one over here, this piece, so this is really that. I'm going to add 1 here, and then whatever's right here, I'm going to rewrite that same thing here. And so this winds up with x squared over 2. For the second one, don't forget we got a little minus right there. What you need to think about right here, let me move this over a little bit so I can have more room to write. When you see this one, it's just a strange little number by itself, you need to think that. Because remember, anything to the 0 power is 1. So when you have a constant, you're going to have to bring a variable back into it. So what happens is the same thing that we did over here. So we have this 3, and then we have x to the 0 plus 1 all over 0 plus 1. So this winds up being just a plain old everyday 3x. And then, don't forget, plus c. And this would be your answer for that one. Okay. The next one, we are going to integrate 1 over 4 x to the 6th minus 5 x to the 3rd plus 9x, and then this whole thing is in terms of dx. So again, we're going to split this up. Now, if you have just a regular number that sits right here, you can actually do this so you don't have to worry about doing anything with that number. And minus 5 with the integral of x cubed plus 9 with the integral. Oops, I forgot my dx's. I hear Keyshawn going, gosh, Miss Calvin. Let's see, plus 9. Ooh, I'm not going to have enough room, am I? Oh, look at that. It's really small, but I got it. All right, so separate them out so that way you can see this. Again, once you get more comfortable with it, then we can go in here and turn around and just do it all in one motion, and you don't have to worry about splitting this up. But sometimes this is actually a huge lifesaver, being able to take that constant number out in the front so you're not dealing with too much. So this is what we know. We've got the 1/4 that's going to sit here. And then I've got x to the 6 plus 1 over the 6 plus 1 minus 5 to the x to the 3 plus 1 over 3 plus 1 plus 9 to the x 1 plus 1 over 1 plus 1. So when I clean this up, I get x to the 7th over, so this turns into a 7. 7 times 4 is 28. Minus, I get a 5, x to the 4th over 4. And I get plus 9x squared all over 2 plus c. And there you go. So when you're doing this, just keep in mind that plus c that has to show up. And that you're keeping everything in order, so that way as you go forward, that you'll get more comfortable with it, and then you don't have to break it down like this. You can actually just wind up doing it. Okay, so let's try this one. So I'll let you do this one. I know it's trig, but use your chart and go back to it and say, okay, we're gonna pull this together and see what happens. So I'm gonna give you a few moments just to play around with it, and then we'll go from there. Okay, so hit the pause button now. All right, here we go. So welcome back. So we've got sine and secant squared. So when we're doing this, we know that these are the derivatives. So we're going to look at sine of theta, d theta, and then minus secant squared of theta, d theta. So that we know this. We know if this is my derivative for sine, this one came from negative cosine of theta. And then if we know that this is secant squared, this is the derivative, we know that that came from tangent of theta. And then plus c. Okay. All right. So now with that, what we're going to do now is we're going to take this information that we've just learned, and we're going to kind of put it together with differential equations. And so what's going to happen, instead of having a plus c as my final answer, I'm actually going to have the real equation. So whereas I have these answers that look like this, I'll actually have a plus or minus an actual number there. So that's the only difference really that we're doing. So here we go. So when I'm looking at this, I've got dy dx is equal to this. Now, when you see dy dx, don't let it panic you, because this is what's really happening. When we deal with this, let me go back and put a slide in here. When I have dy dx and it's going to equal some random function, okay? When I do this, what I'm really going to wind up doing is this. I'm going to integrate both sides, technically. I'm going to integrate this here, and I'm going to have f prime of x dx. So you basically, this becomes a 1, you cross multiply, and that's how you get it. So that way, when I integrate both sides of this, this dy just becomes a y, because you think about it, there's just this imaginary 1 sitting right here. And then over here, this will give me, I don't know what I was trying to write there. This will give me, nope, that's not what it gives me. This will give me this piece right here. So when I take that piece of information and I apply it to this, that's that same mentality that I'm going to be looking at. So I'm going to be I'm going to integrate dy, and I'm going to integrate x squared plus 2x plus 1 dx. So this is what I'm going to look like. So when I do this, I know that this side turns into a y. And then when I integrate this side over here, I wind up with x cubed over 3 plus x squared plus x, and now plus c. So you've done the hard part. But now I want the actual really and truly original equation. So I need to get rid of that plus c. And that's what this right here is for. So I come over here and say, okay, well, if that's really the case, we're going to solve for c. So I get -1. And then I get 3 to the third over 3 plus 3 squared plus 3 plus c. So -1 is equal to, well, 3 cubed is 27 divided by 3 is 9 plus 9 plus 3 plus c. So that's 18, that's 21. So that's -22 is equal to c. So that way when I write my final answer, I wind up with y is equal to x cubed over 3 plus x squared plus x minus 22. And this would be my actual answer. Okay. So again, notice that plus c has to be there because you have to solve for that c value. Okay. If you don't solve for the c value, then you can't get the actual really and truly equation. So this equation right here came from that equation right there. All right. So now, what if they give you something that looks like this? That's okay. What we need to do is you're just going to go back and just do it over again, basically. So what you're going to do is you're going to start off here. We need to get back to the original equation. So if I go back to the original equation, so I'm going to start here. And so I wind up with dy dx. When I integrate this piece here, I get 4x cubed plus c. So that's the first one. So going from here to here gives me that. When I integrate this again, I wind up with y equals x to the fourth plus c1x as your first derivative. And here's your second derivative. So I have these two random values here that I need to deal with. So when I'm going through this problem, I need to be able to solve for both of these. So if when I'm looking at this, I'm going, okay, so now what do I do? So we're going to use our conditions here in this actual equation to actually be able to solve for C1 and C2. Now, use this stuff to your advantage. So you can't use both sets, or you can't use one set for both. You have to use both sets. So what the very first thing that we're going to want to do is we're going to look at this one here first. We're going to look at that set of boundaries. And the reason being is because that x equals 0. Because what I can do is I can say, all right, we're going to go 1. And that's just going to be a 0 plus 0 equals, and then you wind up with C2. So your C2 is equal to 1. See? So now what happens is now we do this. Now we have y equals, and then we have x to the fourth plus c1x plus 1. That's good. So now what we just need to do is we have to go through this again. And now, but because we already used the first one, now we're going to use this second one in here. So we have 8 is equal to 3 to the 4th plus C1x. Oh, not x. I lied to you. 3 plus 1. So we get 8. So that's 81 plus 3C1 plus 1. Extend my page. So this winds up being 8 is equal to 82 plus 3C1. And then when I clean this up, I get negative, what is that, 74 is equal to 3C1. So my C1 is equal to negative 74 over 3. So now when I plug everything back into my final equation, y is equal x to the 4th plus, well, not actually plus, is it? Actually minus 74 over 3x, and then plus 1. So this is the actual equation that you are looking at. Right? All right. So here's you 4 problems to try. So these 4 problems you are going to turn in to Google Classroom. So when you go on there, put those 4 problems in, and this is how I know you actually watched the video. All right, and then I will post the answers to these. Today's Tuesday. I guess I'll post them tomorrow morning, so that way you can see if you've got them right. All right. So that's it. We're gonna stop here. I'm gonna let you try these 4 problems. I can't remember if Khan Academy is up and running on this one or not. Check Khan Academy and see. But other than that, I hope everybody's being safe and everything's going well. And I will talk to all y'all soon. Y'all be good. Stay safe. And yeah, I guess stay warm too. All right. I'm signing off. TTFN. Ta-ta for now.